um, for lecture 2. So I think the lecture 2 notes have just been posted. I have maybe 10 minutes of things from lecture 1 that I still want to cover, and then we'll get into lecture 2. Lecture 2 will be about, at this point, I haven't proved anything. I've done no math. I've made some definitions. Lecture 2 will be about the relationship between statistical physics and combinatorics, and we'll actually prove 2 theorems. And the 2 theorems, pleasantly, are related to 2 other courses you've had or are having. So that will be fun, I think. But before we do that, let's finish a couple things from lecture 1. Also, I'm going to try to write bigger this time. People hinted that would be good. So if I start to write small, just shout at me. So a couple things from lecture 1, just the basics. The way I defined things yesterday, this energy function h was just some general function on configurations. Actually, we care about specific h's that sort of respect the structure of the graph. And so really the kind of h's that we care about look like this. H of sigma, and the 2 examples fit this, but h of sigma is the sum over vertices of your graph, maybe some function f of sigma v. So, you get some function of each of the spins, but you also then sum over edges, and maybe call some function g of sigma u sigma v. So this energy function actually splits nicely according to the graph structure, and that actually gives us some nice properties. I'll say that this is not the only type of Gibbs measure we'll think about in this course. You could also imagine that maybe, so far I've defined things where the spins live on vertices. You could also have spins living on edges instead of vertices. That's perfectly fine. You could also imagine that instead of a graph, you have a hypergraph. And so then, maybe you have u, v, w is a 3 uniform hyperedge, and then you have some function of the hyperedge. Okay, so there's generalizations, but in general, think of this. And if your Gibbs measure has an energy function like this, then actually the nice thing is that the Gibbs measure is a Markov random field. And there's a few different ways to define what this means, and I'll sort of in pictures do a couple. But let's say here's your graph, and here's a set of vertices A, here's a set of vertices B, and here's a set of vertices C that separates A from B. So to get from a vertex in A, you have to pass through C. And the Markov random field property says that the conditioned on sigma C, so this notation just means the spins that live in the vertex set C. So if we condition on those spins, then the spins in A and the spins in B are independent. So if I fix the spins here, then the things that are separated, these are independent. So this is like a spatial Markov property. You can imagine a Markov chain. You condition on what happened your last step, and then the past and future are independent. Here, this is a spatial property. In particular, you could imagine a special case. You just have one vertex and its neighborhood. So the neighborhood of this vertex separates V from the rest of the graph. So if you condition on the spins at of the neighbors of V, then the spin at V is independent of the rest of the graph. And this is actually really, really useful. We'll use it to calculate a bunch of things. So in particular, let's think about the hardcore model. And we can look at, you have this graph, this vertex. And what can happen in the neighborhood? Well, either there's a vertex in the neighborhood that's occupied, right? And if the vertex in the neighborhood is occupied, then V cannot be n, so the probability it's n is 0. But what if, let's say, V is unblocked? meaning the independent set intersect the neighborhood is empty. So what is the probability that V is in the independent set given V is unblocked? So the nice thing is this doesn't depend on anything else, right? Once you condition on the neighborhood, that's all you need to know. Well, there's two possibilities. Either you can be in the independent set, in which case you get a factor lambda, or you can be out of the independent set, in which case it's just a factor 1. And so it's lambda, the factor you get if you're n, over out plus n. Okay, a nice little exercise would be look at the Ising model, the ferromagnetic Ising model, and say that maybe you have 4 neighbors and you have 3 pluses and 1 minus. Then compute yourself what's the probability that V is a plus. Okay, it's the same type of calculation here. So this is very, very useful, and it lets us compute things. And this is a very special property of this type of measure. So imagine I picked, instead of picking from the hardcore model, I picked an independent set of size k, fixed size k uniformly at random. Then we definitely would not have this property, right? Because you have this global constraint on the size of your independent set. You're not going to have independence. So it's a useful special property. Good, so Markov random field property. The other thing I wanted to say is something about dynamics. And we'll say more about this later. So right now I've just described this probability distribution on configurations. But if you imagine like the physical model, like the gas in this room, you could take a snapshot and just say, okay, what's the probability there's molecules at these positions? But also like the molecules are moving around, bouncing off each other, doing all sorts of things. There's some dynamic process that we think in the over long time scales like has the right distribution of the model. And the same thing happens here. There's simple random processes that converge to the right distribution. And the one that we'll think about here is a Markov chain. So Markov chain. And a specific Markov chain called the Glauber dynamics. And so I need to tell you the update rule. So let's say you start at a configuration sigma. Then what do I do at each step? I pick a vertex at random. And then I just resample the spin at V conditioned on everything else. Okay, so I fix all the other spins and I just resample that one spin. And so it's very easy computationally to do this. We just calculated this. So what happens for hardcore model? You pick a vertex at random. If it has a neighbor in the independent set, then you can't do anything. You just do nothing. You leave that vertex out. If none of its neighbors are occupied, then you flip a coin, a lambda over 1 plus lambda coin. If it comes up heads, you put that vertex in. If it comes up tails, you leave it out. Okay, and so that's one step, and then you repeat this again and again. Okay, that you could teach a whole semester-long course just about Markov chains, but I guess I just want to say 2 things. One is that this Markov chain converges to the stationary distribution, which is the Gibbs measure, and you can check it's reversible with respect to this measure. But the more challenging question and very practically relevant question is how quickly? And one way to measure that, and there's tons of stuff about this, is in terms of the mixing time. So this is the number of steps starting from a worst case that you need to get close in some metric to the target distribution. So I don't want to say too much now. I'll say more later. But the point is that you can use this as an algorithm, and it's a very easy to implement algorithm. But whether it's effective or not depends a lot on how quickly this process converges to the stationary distribution. Good. Okay, I think there was one other thing I wanted to say from lecture 1, but any questions about lecture 1 before we move on to lecture 2?
Do you explain the lambda over 1 plus lambda again?
Yeah, good. So you have none of your neighbors are n. And so, you know, whatever is happening here is happening here. There's two possibilities for v. It can be in or out. If I'm in, I multiply the weight of the rest of the configuration by lambda. And if I'm out, I don't multiply it by lambda, or I multiply it by 1. And those are the two possibilities. And for every possible other independent set in the complement, I can multiply by lambda, or I can multiply by 1. And so that's somehow the normalizing constant of this one spin. And the in is this, and this is the total. Yeah. Oh, sorry, this exercise was for easing model. So where you have plus minus ones, and yeah, so I want you to just do that little calculation. Okay, so let's move on to lecture 2, or topic 2. And the first thing I want to do is just put up a dictionary with some statistical physics words on one side and some combinatorics words on the other, just to say that there's like a glossary that you can translate between the two. And I might even say something about algorithms as well. And then we'll state some theorems and actually do some proving. So here's the glossary. So yeah, statistical physics here, let's say combinatorics here. Good. And so on one hand, we have this term, a ground state. So this is in the Gibbs measure, this is a configuration of maximum probability. So the monochromatic configurations for easing model, a maximum independent set for a hardcore model. And in combinatorics, this is like the extremal problem. So find, you know, what's the largest independent set in this graph or hypergraph. One thing that will be nice coming up will be, you know, Mantel's theorem. So I want to start hinting about triangle-free graphs because that will be the subject of the last couple lectures. What's the extremal problem? Which triangle-free graph has the most edges? Well, balanced by complete bipartite graph. Good, ground state. We have the partition function. And here we have counting or enumeration. So how many independent sets are in this graph? Or, you know, here a nice question is, how many triangle-free graphs are there? We have the Gibbs measure. And in combinatorics, we like to think about typical structure. So does anyone know if I pick a uniformly random triangle-free graph, what does it look like? Yeah, with high probability, it's bipartite. It's actually like a random subgraph of a bipartite graph. Yeah, so, but this is in physics, this would be a sample from the Gibbs measure. Notice that, you know, we have something nice in the physics world, which is we often have this parameter beta in the easing model, lambda in the hardcore model, where we're not just counting, but we're sort of tuning this measure for different densities, or we're getting further or closer to the extremal problem. We can do this in combinatorics too. We can ask for, what does a triangle-free graph at this density look like? But I think this is a nice way to parameterize it. Yeah, let's see. Here, this one is maybe a little bit less straightforward, but often in combinatorics we talk about stability. And what is stability? Stability says if you are suboptimal, do you resemble the optimal structure? Okay? And there's many actually very different ways to make this precise. But in a sense, that's related to the question of phase transition in statistical physics. So again, I want to think back to the pictures I put on the board. The pictures on the right, we were picking a random sample from the Gibbs measure. So it wasn't an optimal structure. It was a random sample. It had some defects. But on the right-hand side, the sample actually did resemble the ground state. It was like mostly pink, or it was like mostly even vertices occupied for hardcore. Whereas on the left, it didn't actually resemble the ground state. And so this is a different notion of stability than you see in combinatorics. Combinatorics, often we want to know, like, if you're a tiny bit suboptimal, do you have to be very close in some edit distance to the extremal example? This is like a very, very weak notion of stability. How far can you get away from the extremal example and still notice that there was an extremal example sitting there? Good, so this is some of the terminology. Maybe I want to say a little bit about algorithms too, because this is a third subject that deals actually with very similar objects and has its own perspective. So ground state extremal problem, for algorithms, this would be optimization. So given a graph as an input, find a maximum size independent set. In general, that problem's NP hard, but other models, it may be not hard. Counting and enumeration, this is also an algorithmic problem. Usually, for this type of problem, the right algorithmic problem is approximate counting. So given a graph, the algorithmic problem is to approximate the count or the partition function up to like a 1 plus or minus epsilon multiplicative factor. And depending on parameters, this might be hard or easy. What's the algorithmic problem associated to the probability measure? Well, it's sampling. So, these Gibbs measures are very high-dimensional probability measures. The state space is exponentially large, but the specification of the measure is actually small, right? So I can, it's a graph. It's the size of the graph, polynomial and the number of vertices, whereas the actual distribution has exponential size. And the question is, can you still sample efficiently, polynomial in the size of the representation as opposed to the size of the support? So that's an important algorithmic problem. And then, okay, this is not such a tight analogy, but there's a notion of computational threshold. So depending on your class of graphs and your set of parameters, it might be that for some parameters, these problems of approximate counting and sampling are tractable. There's polynomial time algorithm. But as soon as you change the parameter a little bit, all of a sudden it becomes NP hard. And it turns out that for some of these models, the computational threshold actually occurs at the same point as a physical phase transition in the statistical physics world on a certain set of graphs. That's another very interesting subject, but just keep that in the back of your mind. Good. Okay, any questions about this dictionary? Good. Okay, so I'm going to state a couple of combinatorics theorems, and then we're going to prove them. And yeah, as I said, they're related to the courses you've been taking. So two combinatorics theorems. So theorem 1, and this is by Jeff Kahn. If G is a deregular bipartite graph on n vertices, and let's say 2D divides n, then the number of independent sets of G is at most the number of independent sets of, well, let me write KDD to the n over 2D. So KDD is just this complete bipartite graph. D vertices. And this is saying that, and if you take n over 2D disjoint copies of KDD, the number of independent sets multiplies. I think that was an exercise yesterday about multiplying partition functions. And so it's saying this graph that consists of a disjoint union of complete bipartite graphs has the most independent sets of any deregular bipartite graph. So maybe Jin-Young Park stated that theorem. Good. There's some extensions. So Prasad Tedali and David Galvin and then Yufei Zhao both extended this theorem. And you can get rid of the restriction on bipartite. And then you can also actually not just talk about counting independent sets, but you can talk about this weighted count, the hardcore partition function. And so the more general theorem by Kahn and then Zhao and Galvin and Tedali is for all deregular G on n vertices, 1 over n log hardcore partition function is at most 1 over 2D log of the same for KDD. Okay, this is just, I like this way of normalizing things. Then you don't have to talk about dividing by and things like this. This theorem definitely implies that and is stronger, the weighted things. So this is an extremal problem for regular graphs. This particular graph, KDD, maximizes this independence polynomial once you normalize the right way. Okay, so that's, maybe I'll call this is theorem. This is theorem 1. So theorem 2, and this is by Shearer. And his theorem is the following. If G is triangle free, and has average degree D, then I'll say 1 over n times the independence number of G. So this is the size of the largest independent set, and I'm just normalizing by to make it the density, is at least 1 plus something that vanishes as D gets large, log D over D. So you all know the theorem that says if you have a graph of maximum degree D, then your independence number is at least, or density is at least 1 over D plus 1. What this theorem is saying is if you're triangle free, you get better. So Aitai-Komlosh and Simoretti got the log d, but with a small constant. The point of Shearer's theorem is getting this constant 1. And so this is, I think Julian promised that I would prove an upper bound on R3K. So this is an upper bound on R3K, and I'll just say why. So for an upper bound on R3K, you need to, in a triangle-free graph, you need to find a large independent set. And so you give me a triangle-free graph, and I say, well, is the average degree large or small? If the average degree is small, then I apply this, and I get a big independent set, right? And if the average degree is large, that means I have a vertex of large degree in my triangle-free graph, but the neighborhood of a vertex in a triangle-free graph is an independent set. Okay, so as an exercise just to set those two expressions equal to each other, the size of the independent set you would get by this bound and the size you would get just by D, the neighborhood. And when you set them equal, you get the bound on R3K, which is one k squared over log k. So this 1 is this 1 here. Good, but the nice thing is both these theorems have some similar form, right? You have something to do with independent sets, and you want to either maximize or minimize over your set of graphs. Here are just regular graphs. Here's triangle-free graphs of bounded average degree. Yeah, so they're nice theorems, important theorems. What we're going to do today is we're going to reformulate them in terms of the definitions I've given you about Gibbs measures and partition functions, and then we're going to prove them just using one proof. Okay? So I think that's kind of cute and fun, and I'll finally do a proof and show you that these definitions are somewhat useful. Good. So I'll state the theorems, and these are both joint work with Ewan Davis, Matthew Jensen, who's here this week, myself, and Barnaby Roberts. So this, when I was at Birmingham, the other three were PhD students at LSE, and we had a very fun few years of working together. So two theorems. One theorem is, okay, so over here, maybe I'll do a definition, or maybe I'll state the theorem and then say what the definition is. For all d regular G alpha bar G of lambda Okay, so this alpha bar, this is the occupancy fraction from your exercises yesterday. This is just the expected size of your independent set from the Gibbs measure divided by n. Okay. And what this theorem says is for any d-regular graph, if you pick a random independent set from the hardcore model, the expected density, the occupancy fraction, is bounded by KDD. So that's the theorem. This actually is a stronger theorem than this. Yeah?
You mean the occupancy fraction of KDD?
Yes, good, thanks. That's not G. Good, thank you. Yeah, thanks. So why is this a stronger theorem? It's because we can, the one thing I showed you yesterday was if you take a derivative of the log partition function, you get an expectation. But the other way of saying that is if you integrate an expectation, you get a log partition function. So let's just do this. So we want to derive theorem 1 from this theorem. So I don't know, maybe that's theorem 2, this is theorem 3. 1 over n log z of lambda. It's the integral from 0 to lambda of alpha bar g of t over t. Remember the identity I'm using is lambda log z prime is the expected size of the independent set. So I have to divide by t to get rid of this lambda. Dt. Okay, so to get the log partition function, you integrate the occupancy fraction from 0 up to lambda. But this is, right, this is at most integral 0 to t alpha bar kdd of t over t, which is 1 over 2d log. Okay. So it's kind of surprising, right, that, you know, here we're talking about the count or the partition function. It's some exponentially large count. And here it seems easier, right? At least you're just talking about estimating an expectation. But yeah, so that's theorem. That's one theorem. And then the next theorem, yeah. Because I mean, you know, if a function is bigger than the other, that doesn't mean that its derivative is bigger, right? Like you can't go from here to there. It's a stronger way of saying, you know, f is bigger than g is to say, you know, they start at the same place and f prime is bigger than g prime. That's a stronger statement. Yeah. I mean, there are examples where this theorem holds and that theorem's false. Yeah, different models. Oh, I probably shouldn't have erased that one, just so you could compare. But theorem 4, if G is triangle free and has max degree D, then alpha bar G of 1. So this is just the average density of a uniformly drawn independent set. Is at least 1 plus little o d 1 log d over d. So this is saying you have a triangle-free graph of maximum degree d, and you pick a uniformly random independent set, and its density on average is 1 log d over d. So notice it's like the max and average from Shearer has flipped. Shearer was for average degree, and then the max independent set is of this size. This is max degree, but you get the average size. And this theorem is tight. So this one is tight, and the example is a random deregular graph. So the average size of an independent set for a random deregular graph is 1 log d over d, but the max size is 2. So for all we know, Shearer's theorem actually could be improved by a factor 2, which would then improve the R3K bound down to 1/2, getting closer to the 1/3. That's the lower bound now. Good. So questions about these two theorems? This theorem also, in the same argument, would imply the R3K upper bound. You can do the same thing. Yeah? Why are you dividing by n and 2d? Oh, because the derivative of log z is not the expectation. It's lambda times the derivative of log z. That's the expectation. And so the derivative of log z is expectation over over lambda. Yeah. Yeah, it's just the way things are parameterized. OK, so what I want to do now is prove these theorems with one proof. I'm going to make one simplification, and then at the end I'll tell you how to undo that simplification. And the simplification is I'm going to assume in both cases that I'm deregular and triangle free. So this theorem doesn't say triangle free, so I want to get I'll tell you how to fix that. Here it says max degree d, but it's an easy fix to go from regular to max degree. But it'll be deregular and triangle free, we'll assume. So good. So G is deregular and triangle free. And what are we interested in? We're interested in this occupancy fraction. Good. So what I want to imagine is a two-part experiment. And what's going to happen? I'm going to pick a vertex uniformly at random. And I'm going to pick an independent set from my Gibbs measure. Okay. And then I'm just going to record some data about this independent set from the perspective of this random vertex. In particular, what I'm going to record is a random variable y, which will be the number of unblocked neighbors of V. Okay, unblocked means a vertex doesn't have any neighbors in the independent set. Okay, so if my picture looks like this, here's V, here are my neighbors, and they have some neighbors. If this vertex is in the independent set, then this vertex is blocked, but maybe none of these vertices are in the independent set, and so V would have two unblocked neighbors. If V itself is in the independent set, then V has 0 unblocked neighbors, because V is blocking. Okay, so that's this experiment, and then what I want to do is I want to write this alpha bar in terms of statistics of y. Okay. So I'm going to write up some facts, and these facts are all these facts that I'll write up are just using this Markov random field property that I wrote up to start the day. Good. So facts. 1. Probably V in the independent set given V unblocked is lambda over 1 plus lambda. So that we saw already. I mentioned that. 2, what is the probability that V is unblocked given that V has J unblocked neighbors? Okay, so what I'm saying is here's the picture. Here's V. Maybe V has some vertices, some neighbors that are blocked, and then some neighbors that are not blocked. And I want to know, given that V has 3, for example, 3 unblocked neighbors, what's the probability that V itself is unblocked? Okay, so let's think about this a bit. V being unblocked just means that none of its neighbors are in the independent set. And I don't have to worry about these guys, because these guys are blocked. They can't be in the independent set. I do have to worry about these guys. They could all be in the independent set. And what are the possibilities for these guys? So they're unblocked. And crucially here, this uses triangle free. So this is the one place we'll use triangle free. There's no neighbors between them. Yes? I'm blocking? Can you see it now? Okay. Okay, great. Yeah, so you want no neighbors to be in the independent set, and because it's triangle free, there's no conflicts among them. So what are all the possibilities? Actually, any subset of them could be n, right? And what are the options here? There's a 1 or a lambda, so 1 plus lambda. Well, these are disjoint, so 1 plus lambda, 1 plus lambda, 1 plus lambda. And what is the weight of the configuration that we're interested in? Well, it's the completely unoccupied configuration, so that's 1, 1, 1, 1, 1. And so I'll write the answer, and then you can think about it. It's 1 over 1 plus lambda to the j. Okay. These are all this is the weight, it's the count, but it's the weighted count in our partition function of all the possibilities of the neighbors, 1 plus lambda to the j, and we're only interested in the one special configuration that has weight 1, where it's unoccupied. Okay, so if we're happy with those two facts, then we can write some formulas. Okay, so remember this two-part experiment, I'm picking V at random and picking the independent set at random. And so I want to write a formula for alpha bar g of lambda. Well, this is probability that V is in the independent set, right? Because V is a uniformly chosen vertex. So this is the same, which is lambda over 1 plus lambda times the probability that V is unblocked. Right, that's fact 1. And then, well, probably V is unblocked, I can condition on y, the number of unblocked neighbors. So y can be 0, y can be 1, up to d. So this is lambda over 1 plus lambda, sum j equals 0 to d, probability y equals j. And then if I have j unblocked neighbors, well, fact 2 says the probability I'm unblocked is 1 plus lambda to the minus j. And this is just a funny way of writing an expectation. So this is lambda over 1 plus lambda, expectation of 1 plus lambda to the minus y, this random variable. Okay, so that's just some identity that this occupancy fraction can be written as the expectation of an exponential in this random variable y. Good. Let's write another formula. So the occupancy fraction, a random neighbor of a random vertex in a regular graph is a random vertex in that graph. So the occupancy fraction is also 1 over d times the expected size of the independent set intersect the neighborhood of V. So this is just the expected number of neighbors of V that are in the independent set. right? But this by fact 1 is just 1 over d lambda over 1 plus lambda times the expected number of unblocked neighbors of v, but that's y. Okay. Good, we're almost done. Any questions about these two facts? So these are just identities that hold for any deregular triangle-free graph. Triangle-free is important when we derived this formula, this 1 plus lambda to the minus j, use triangle-free.
You use triangle-free just to say that they're independent because there's no way between them.
Yeah. At the end, or maybe in the exercise session, we'll say, okay, how for theorem 3 can we adjust that? Yeah. Good. So what do we have now? So yeah, so let's write this identity. It is, we can write it like this. Expectation of 1 plus lambda to the minus y equals 1 over d expectation of y. Right? And this is a constraint. We can think of this as a constraint. And what do we want to do? We want to, well, for one of the theorems, we want to maximize alpha bar, right? That's the theorem 3. And the other we want to minimize. Okay, so that we have optimization problem and we, over all graphs, and we want to maximize or minimize. So one thing that you do in optimization often is, you know, the set of possible solutions here is very nasty. It's all triangle-free graphs, all random variables y that come from some triangle-free graph on a deregular triangle-free graph on some arbitrary number of vertices. That's the set of possible solutions here. So what do you do in optimization when you have sort of a nasty set of feasible solutions? You relax the problem. You expand your set of possible solutions. So what will we do? We'll relax the optimization problem to all random variables y that are bounded between 0 and d and satisfy the constraint. So not all random variables y, you know, that have this property come from a graph, but that's fine. As we just want upper and lower bounds. Okay, so this is the optimization problem, right? We want to maximize or minimize expectation of y subject to this constraint. Maybe I'll call it star. Star holds, and y is between 0 and d. Okay? So let's, which do you want to do first? Maximization or minimization? Okay, let's do minimization first. No one shouted. So minimization is quite easy. It's just Jensen's, not Matthew Jensen, but Jensen of the inequality, Jensen's inequality. So expectation of 1 plus lambda to the minus y is at least 1 plus lambda to the minus expectation y. And so what does that say? That's Jensen. That says that the minimizer is the constant random variable y, where we have 1 over d times y equals 1 plus lambda to the minus y.
To do the minimization, you didn't have to use the relaxation form, right? You just, yes.
That's true, yeah. But I like to think of it as optimization, but you're right. You could have that could just be a line in the proof. Good. And you can solve this. This gives you some value. I think I plotted in the notes. So this, yeah. So let's call this y star. And so what is the theorem? This says that alpha bar g of lambda is at least lambda over 1 plus lambda, 1 over d y star. So that's the theorem. Why does this look like log d over d? Well, it actually doesn't really. You plot this y star as a function of lambda, and it goes like this. And then for some funny reason, it is non-monotonic. It goes down, which is strange because we know from your exercises that this function is monotonically increasing. And so what do? We just say, we pick some value here, like, I don't know, 1 over log d or something like that, and we stop it there. So if you plug in 1 over log d and solve this equation, so if lambda equals 1 over log d, this right-hand side is 1 plus little o1 log d over d. And so plugging in 1 over log d gives the theorem. But that's just some calculus. So that's theorem 4, right? Theorem 3, so now we want to maximize. So you can think a little bit about how to maximize, but you have this random variable that's bounded between 0 and d. It has a constraint that says that its expectation is equal to the expectation of an exponential, and you want to make the expectation as large as possible. So you can play around with it, but what you'll realize, does anyone have a guess of what the optimizer is? So it's not constant. That was the minimizer. So what's sort of the opposite of constant? Yeah, someone in the front row made a sign like this. That's right. So the maximizing distribution, y, is supported on 0 and d, the two extremes. And this somehow makes the expectation of the exponential large, and so it maximizes. OK, that's cool. So, and there's a unique distribution that satisfies the constraint for a given lambda and d that's supported on 0 and d. OK, but why is that nice? Well, remember our target was KDD. What happens in KDD? I pick a vertex. Here's my v, like here. And then I want to know the number of unblocked neighbors. Well, two things can happen. Either some vertex on the left is occupied, but it's complete bipartite. And so if this vertex is occupied, then all of these are blocked. And so y is 0. And if nothing on this side is occupied, then everything's unblocked. And so d. So this supported on 0 and d, and this is the distribution you get from KDD. And so that's the maximization proof. So really, it's once you set up that funny identity, it's really the same proof. Of course, there's some tricks, but really the tricks were just basic identities with these Gibbs measures, like the integrating, the Markov random field property. Yeah. No, so you have to, the steps are, the steps are correct. It was, the probability V is in the independent set, is lambda over 1 plus lambda times the probability V is unblocked. That's correct. So we need to write what's the probability V is unblocked. Well, I can condition on the number of unblocked neighbors. But we're not like associating the events. We're associating these probabilities. So that's the key thing. I'm making an equality between probabilities. You're right if you like try to say, here's the event that something happens, but that's not what I'm doing. Yeah, we can talk about it in the exercise. So in the last one or 2 minutes, I just want to say, how do you extend the proof of theorem 3 when you're not triangle free? And that goes back to this, this 1 plus lambda to the minus j thing. So instead, now I have my vertex, but now I might have triangles in my neighborhood. And some of these vertices might be blocked. But then maybe some are not blocked. So these are my unblocked neighbors, but they have a graph on them. Okay, so what is the probability that V is unblocked given that H is the graph induced by its unblocked neighbors? So the graph induced by the neighbors when it was just J and triangle free was J isolated vertices, but here we might have an actual graph. Okay, so what is the probability it's unblocked given that H is the graph induced by the unblocked neighbors? Yes, exactly. So the answer is it's 1. We want this empty independent set over the total weight of all the possible independent sets, but that's just the independence polynomial of H. So this is the identity that replaces the other identity. You also have to say what's the expected number of neighbors there, and that's something like lambda z h prime over z h. And then you have a new identity, but that's in terms of expectations of partition functions of h. It gets a lot more complicated, but in the notes, I explain how you solve solve the upper bound optimization problem using this and linear programming. So if you're interested, follow in the notes. I won't say more about that, but that's it. So thanks. And then we can discuss anything you want in